Alright, so this video is going to cover rational expressions as an equation. So let's look at that topic. So equations with rational expressions. Alright, so let's look at my first example here. What I wanted to point out also is the method that I use is the common denominator. You just get rid of your fractions. You're going to multiply by the common denominator. So that's my process. So you're going to multiply by common denominator. And this is a pretty common practice with this one on the solving. So let's look at my first one. So if I have 2x, or 2 over x, minus 3 halves equals 7 over 2x. So here's my first rational expression, or rational equation. It's not really an expression when it has an equal sign, it's then an equation. So when we look at this, we could combine the like terms here or get a common denominator, subtract them, and there'd be a lot of steps with each process because it has fractions. The best way is to multiply everything by the common denominator and get rid of all denominators. So all the denominators are x, 2, and 2x. So if we combine that idea, if we have 2x as our common denominator, that would include the 2 and the x. So whatever you have in common, you only have to take once. So we have the 2 and the x. So I'm going to multiply by 2x. So the common denominator is 2x. So I'm going to take 2x and I'm going to think of it as over 1 times the first fraction, 2x over 1 times the second fraction, and 2x over 1 times the last fraction. So make sure that you multiply it by every single term in your equation. Now watch what happens. This x will cancel with this x. 2 times 2 is 4. Minus, so I did reduce this whole one. 2 cancels with the 2. X times 3 is 3x equals 2x and 2x cancel all the way. You're left with just that 7, or 7 over 1. So you have 7. Now solve this. So I'm going to minus the 4, and I'd get negative 3x equals 3. Divide, and I get x is equal to negative 1. I would love it if we're done. But we're not done with rational expressions. So we have to check this answer. That's really important. Sometimes they make 0 in the denominator and sometimes they just don't work. It depends on the problem. If we go back up here, if we put a negative 1 here or here, we don't get a 0. So this one actually does work, and this really is the solution. So be careful if one of them ends up not being a solution. All right, so there's my first example. What if I have 2 over x minus 3 over x plus 3 equals 12? This is one I always see show up on everything. I don't know why. One similar, I guess. Okay, so we have a fraction. Look at this as x minus 3, x plus 3, and then what's this going to factor into? It's going to factor into these two, right? So really, if I take x minus 3 and x plus 3, I'll incorporate all denominators. So my common denominator is going to be x minus 3, x plus 3, because this factors into that, right? So we're going to take x minus 3, x plus 3, and this is probably more writing than I would, if I'm doing it, I'd probably write it here, but I have to write it out pretty for you. So think of this, we're going to multiply by that common denominator over 1, however you want to think of it, times the first fraction, minus the x minus 3, x plus 3 over 1 times the second fraction. And then it's going to equal this one, x minus 3x plus 1, or x plus 3 over 1 times my last fraction. And I just multiplied or factored this one out here. Okay, so I just changed this one to what it in its factored form. I can almost barely fit this entire ugly mess on my screen here. So once we've written our common denominator, then we can cancel the common factors, right? And we'll have no more denominators. So cancel here, and you have 2 times x plus 3. So I'm going to multiply that out, and I'd have 2x plus 6. So make sure the 2 is being times by both terms. Bring down the minus sign, and you're going to, these ones will cancel here, and you're going to have 3 times, this one I'm worried about the way I'm writing it that I'll confuse you, but 3 times x minus 3, but you're minusing the whole thing. So I'm going to put a parenthesis here so that I could think of this as 3x minus 9, but you have to subtract off each term. So I'm going to keep the parenthesis so that I remember to distribute that minus. So when there's a minus involved, that's why I picked this one, you have to be super careful. Over here, everything will cancel, thank goodness. So I just have 12. Okay, let's distribute this and add our like terms over here. So I distributed my negative, so see how it changes that 9 sign? That's what most people would miss, and then you of course miss the rest of the problem. So 2x and 3x minus 3x is negative x. 6 and 9, 6, why couldn't I add that in my head for, I don't know, but we get 12 equals 12. Or 15. Goodness gracious. I was like, no, that's wrong. I can't add today. I guess I need to go back to bed or drink more of my coffee. Okay, so 6 and 9 sometimes make 12, sometimes they make 15. Then from here, I'm going to minus the 15 over. I was like looking at it weird because I was like, I know that's not the answer. So negative x equals 12 minus 15 is negative 3. We can't keep a negative x, so we change our signs and we get x is 3. Yay, we're done. That was a lot of work to get 3. Now check this answer. Go back up to the original problem. If you put 3 here, do you get a 0 in the denominator? Why, yes, you do. So this is actually an extraneous solution and it can't actually work. So you really have no solution. There is no way to know at the beginning of a problem if you are going to do all this work for a no solution. All right, so it's just kind of the way it is. So unfortunately, that one doesn't work very well. Okay, so that is a pretty common problem. Sometimes you'll get a problem where you have 2 answers and one works and one doesn't. That's pretty common as well. Let's look at in this equation section, they do a couple problems where you graph these. So I'm going to graph a couple for you. Let's look at the parent graph first. So the parent graph would be f of x equals to 1 over x. Just 1 over x. Pretty basic. That's our parent graph. And our domain is going to be anything but 0. We can't have 0 in there. So we're going to have an asymptote at 0. And what an asymptote is it's a line you can't ever be on if you're that graph, right? You can't ever be the 0, so you can't ever be at that spot. So here's my x, here's my y, and I'm going to use my highlighter here to make a dotted line down my asymptote. You can't ever be, oops, I didn't even explain that there's 2 asymptotes, but I will, hang on. You can't ever be where x equals 0. Well, where is x 0? It's going to be along the line x equals 0, which is here, a vertical line. And then you can't ever get 0 out, so y can't ever equal 0 as well. So you end up being not able to cross x is 0 or y equals 0. Okay, so remember, horizontal is y equals 0. X is vertical. So those are our 2 asymptotes. Then from there, we can put in a little chart and get out numbers. We can think, okay, so x, y, right? X If x is 1, then y is 1, because 1 over 1 is 1. If x is 2, y is 1/2. If x is 3, it's 1/3. And you can see it can get smaller. Let's put in a couple negatives. If x is -1, you get -1. If x is -2, you get -1/2. And let's graph that kind of idea that we have there so far. So 1, 1 would be here. 2, 1/2 would be here. 3, 1/3 would be here. And then you could get 4 and a fourth, and you could kind of see the pattern. -1, -1 would be about here. And -2, 1/2 would be here. And if we did -3, 1/3, -1/3, we get that. And you could kind of see the graph. I'd like to see more what it does here, but this is what the graph should look like. Okay, so what it's doing is it's getting really, really close to that asymptote, because you can see the fractions will get smaller and smaller and smaller, but it never actually gets to 0. It can get really close. You can have 1 over a billion, right? But it never actually touches it, and that's how the asymptotes work. So this is our parent graph. This is what they mostly look like. Let me exit out of my viewer here, and I'm going to show you on a this is just a graphing calculator that I have for one of my textbooks. I don't have a handheld one, like a TI, that I can show this on very easily. So let's put in 1 over x. We know that the graph looks like our paper that we just did. Now look what it does. It draws this weird line here. That line is actually not part of the graph. So you have to know what you're doing. So 1 over x, or how to read it on a graphing calculator. You can see it's going to be going close, close, but it's never going to get there. And the same idea here, okay? And you kind of have to ignore this weird line. Now notice over here on my chart that it does of my equation that 0 is missing 1, but then you have all the other numbers, okay? So for my next example, why I have this still open, what if I subtract 4, and I bet I need a parenthesis around that or it might not work. Okay, what if I subtract 4? What did it do to my graph? It moved it to the right 4. What if I would have added 4? It would have moved my graph to the left. So if you in the denominator add or subtract, it goes the opposite way you would think, just like when you square something and you're using the number in the square to move your vertex. It does the opposite this way that you would think it would do. It's going to move it to the right and left, positive to the left, negative to the right. Now what if I then took and added 5 out here? What's that going to do? Okay, well, maybe I should just do like 2. Then you might be able to see it a little bit better. Okay, so what you can see is at 2, right, up here, you can see it moved it up. But it's a little hard to see on this graph because, again, it has this weird line. If it just drew it normal. One of my TI-89, I believe, does draw it without the weird line. But anyway, so you could see if you add a number on the very outside of yours, it's going to move you up or down. What if it was a minus? Then it's going to move you down. So what I love about a graphing calculator is you can actually learn what the numbers do to your equation. You take your general basic equation, parent graph, and you play with it. What happens if on the parent graph I had a 5 up here? What did it do? Kind of separated it out more, right? It stretched it. Okay, so what if you did a number right here? I don't think it read that correctly. Hang on. I was like, yeah, it doesn't form a line. Okay, there we go. So it pushes it in. It compressed it more. Okay, if you're thinking about depending on how you're looking at it. But okay, so it either is going to make it closer, or so faster it gets close to those asymptotes, or it just spreads it out. So you can play with the numbers, what they do a little bit on a graphing calculator, which is what I love about them. Let's go back here. So if I was to take, here's one that I did on my other paper. It might be a little too shiny, I don't know. Yeah, it's too shiny in there. So what if I did 1 over x minus 4? So 1 over x minus 4. We know it's the opposite when it's down here in the denominator, so it's going to move my asymptotes from 0, 0, and it moves that 0, 0 spot over 4. You still have the asymptote of 0 here on the x axis, which is y equals 0, because you still can't get out the 0 for the y. Basically, we didn't add a number over here to move that asymptote. Okay, so we still have the same general graph. So you should be able to generally graph these things just by moving that vertex and being able to see, or not vertex, but that's kind of how I think of it, the vertex of the two asymptotes. I move it around. Okay, there was a number out here, it moves it up and down. The number down on the denominator with the x moves it left and right. Then you can do a chart and easily get exact points on both sides of where that moved to. All right, for the graph. So that is the idea. If I would have put a negative out front, I should show that on the graphing calculator, you would switch quadrants. Okay, so that's another thing that you could end up doing too. All right, so that ends this video. AB.